for the course. So I hope I can wrap things up. Let me just remind you what we did last time. Just so we were in the middle of proving a theorem that gives us some little growth for the solution of the NLS. So let me just remind you of some steps. So we start with this. U0, and the goal is to, by the way, I should remind you that here x is T2, and this is just the square torus. And the goal was to find an initial data that it's small, and so we take S, which is greater than 1. So our initial data, so we want to find U0 such that U0 HS is less than a sigma, and prove, or such that, and if U is solution of NLS with this U0, we can show that there exists a time t very large such that this norm at t is greater than k. Okay, sigma is fixed small, k is fixed large, and then you want to do this. So last time we ended up doing a bunch of reductions to this system, and we came up with a toy model that we hope will represent most of the growing dynamics of this system here. And the toy model at the end of the day looked like this. Maybe I should just write it. Okay, had I b dot j equals minus bj square bj plus 2 bj minus 1 square bj hat, and then plus 2 bj plus 1 square bj hat. And there are some boundary conditions, b0t equals bn plus 1t, which is 0. And initial data, b at t is, b at 0 is some, bj at 0 is some b0j. Anyway. And the way we came to this system was by assuming first that we only consider resonant interaction here, and then within the 4-wave interaction, which are basically vertices of rectangles, we picked a special set that I show you that something like this. Start here, then takes this, then picks up this one, and so on, and expands like that. Okay, so now we say that we analyze this system here, and we use the fact that there is conservation of law, in particular conservation of mass, and if we normalize the mass to be 1, then the whole dynamics, let's call WT, the wave solution map, then and sigma to be the sphere, if you like, x1, xj in Cn such that xi square I1 to n is 1. This is the mass is 1, and since everything is conserved, this solution map is going to map sigma into itself for each time. Going to sigma. By the way, there is no problem here for existence of solution or anything like that. It's a finite system, so it's all easy. And moreover, if we call Tj these big circles, so this is going to be 0, 0 everywhere, except at time j there is a b, and this b j as size 1. So there are these big circles, and last time we said that there is a theorem that tells us the following. If I'm close to, there is T1, T2, let's say T3, I'm close to that, so I pick an X3, then there is a W cap rho, let me use a different name because it needs to be rescaled, so let me just do that. That sends this guy close to, let's say, Tn minus 2 to this point, which is W tau X3. And this is really the forward cascade, because these are low frequencies in the sense that sits in the position 3 and goes to high frequency, which is position n minus 2. OK, so that was from last time. Now, we would like to do, of course, transfer this result of the toy model back to the original system. But before doing that, which is via some kind of stability lemma, I want to talk a little bit about using this result in order to show that you have a solution of the toy model enlarged, not just the one that it's at the level of this frequency lambda n, let's say a big set lambda n, but a little bit larger. So what's happening is the following. If we do these constructions, you see there is parameter n. And this set, where all the frequencies live, it can be enclosed in an annulus like this. So here are all my frequencies that act for that system there, and I'm going to call a lambda n. Okay? Now, you can think of n to be a sequence that grows to infinity. So let me call this n1, and then you can repeat the construction for larger and larger annuli. So let's say there is a much larger one here. And here there are the same kind of construction, but now with a different parameter. Let me call nk. Now, this n1 and nk, how do you pick that sequence? Well, it has to be such that the distance between these two sets is far enough, so that the dynamics does not interact. Whatever happens here is not going to affect what happens here, because the problem otherwise will be that the possible growth is going to be cancelled. Using these ideas, then there is the following theorem. This is in the paper of Hani, Posadeur, Zetkov, and Vishilia. So what do? Well, let's take the whole resonance system. So let's take the following. So I'm going to call R nonlinear, Schrödinger, to be the resonance system, which I write in terms of Fourier coefficient. And basically is this, up to some little gauging, it doesn't matter. And now I'm going to tell you what gamma n is. Well, that's all the frequencies are in resonance with n. So this is n1, n2, n3, such that n2 minus n3. And we are in a square torus, so you have that this is equal to 2 square and 3 square. So it's really the resonance set. OK, so n1, n2, n3. Here you don't have e to the I t omega, because omega, which is what I called, let me write it like this. I call this omega. That's 0. OK, and then at time 0, let's call this guy A0n. OK, so let Rs to be this, which is really fundamentally the resonant part of the original NLS. Let me define, so let me just, let's call the norm of a sequence AN. Let me just make this, it's easier. Let me call A to be this sequence. And then the norm of this A in what I call little hs, well, this is not really nothing else than really the hs norm, but red in the Fourier coefficient. So this is nothing else than sum in n to s, this Japanese bracket, and then an square. This is square root. Okay, so let's make this definition. All right, so then they prove then there exists an epsilon 0, greater than 0, such that for all epsilon less than that, there exists an initial data, a sequence of initial data, with this norm HS. Okay, you know, the notation is a bit wonky, but it's less than epsilon. So small, so you can you fix an epsilon, well, there is an epsilon 0, such that for any epsilon less than that, you can construct an initial data, which has this norm less than epsilon. And when you look at the solution, and there exists a sequence tk, tk goes to infinity, k goes to infinity, such that the solution A and T of my resonant system of resonant NLS has the norm in this sequence, in this HS. By the way, I didn't say, but the S here is greater than 1 as usual. And maybe even greater than a certain S0, I'm not quite sure. But it doesn't matter, S is large for us. And this norm is greater than exponential of a constant log tk to the 1/2.
For S equal 1, you have the energy model.
Yeah.
So that could be different, isn't it?
Yeah, for S equals 1, everything is
so
bounded.
S has to be strictly logical.
Yeah, strictly logical. So, but I'm not sure if it's exact. You can do this for S just strictly less than 0. It might be strictly less than some number.
Last time 2 nodes?
Yeah, that's very good point. Thank you. In fact, this was my next report. The thing is that this is the resonance system. Last time I stated for the full system, but in the domain R cross TD. So when you do that passage from the resonant to the thing, you lose that. But that's exactly right.
Is there any quantum statement for how often TK? How separated TK is?
Yeah, there is some statement like that, and you can read it, and I just didn't copy from the paper, but there is. It also depends on how far these things are, so things are connected. Yeah. So this was just what Peter was saying. I'm not going to rewrite that theorem that I stated last time, but that one was about taking the full system and crossing your torus with R, and then being able to take this result for the resonant part and push it to the full NLS with the loss of a log here. So I'm not going to go to that. And of course, I'm not going to prove this, but it is the construction that we did last time, plus making sure that you can take this annuli, which are farther apart from each other. Okay, so just a little thing. Remember that this is for the square torus. You can do it, so you can use this fact and go up in dimension. This was just 2-dimensional, but you can do now for any d greater or equal than 2, because you already have this base fact. So you just want something that grows, so you can use the 2-dimensional growth to bring it to a higher dimension. Another thing that I want to remark is that I said that the growth dynamics, so that, for example, you can ask whether this fact is true for tori that are irrational, but you can approximate it well with rational number, because the toy model, this first part here, is actually possible to do in that case by using a perturbation of the torus itself. But then when you have to do this argument, you have two kind of approximations. You have the n, well, you have for each, so you approximate your irrational torus with something which is rational. And so you have that sequence that is going towards the irrational number. For each element of that sequence, you have these constructions. So you're going to have a double sequence here. And it's much more delicate than what you might think to take this result and extend it to the rational tori that are well approximated. We are working on that. We should be able to do it, but it's more delicate. OK, now to go back.
Well, can you say a few ideas on how this is closed?
This one?
This result, yeah.
It's exactly using.
So you are using the,
yep.
the model,
and the
model.
Yeah. And then you have to, so the Doi model only gives you, with a parameter n, and it gives you some limited growth. So you'd only go from, let's say, from here to here. But you don't grow more than that. But by doing this construction here.
To pass from the toy model to the result.
OK, so it's a concatenation of toy models.
Okay.
That's what it is, really. You can rewrite, you make it act, you excite only the, so you are not proving that this is true for all solutions of that resonance system. You are proving that there is one solution, right? So you will restrict all the resonant quartets into living on this annuli.
So you write it as a limit of this time.
Exactly.
That's very interesting.
Yeah, that's how it is. It's a very interesting proof in there. OK, so now I wanted to go back to our original question, which was this that I state here.
Well, in the original proof, you had something similar, I guess.
But we had just one step of this. We had only this one.
Okay.
We didn't have it. This came later.
So
Yep.
the constancy on the orbit,
Yes, yes.
the fact that the B's represent the solution for the
Correct.
A, that thing is broken once you go to more than one, and then the interaction, the distance between them helps you.
Has to be very big. I mean, has to be appropriate so that you
Because
don't.
it's no longer constant on,
Yeah.
on the level sets of B's, the A's are constant on one, constant on the other,
Right.
and they're not constant anymore across.
So you had to, because you had this thing interact,
Right.
and you had to make sure that.
So it's a
that
different.
yeah. So the paper is, it's very clever. So, but when we were proving that theorem that I mentioned, like you start small and you end large, we didn't do this concatenation of toy models. We just stayed with one toy model, and so to go back to the original statement, we used stability lemma. I'm going to just state.
Original paper, there was no motivation to even try to make the sequence go to infinity because you can never transfer that result on a
Exactly.
to the global result.
Correct. So exactly, this is exactly the limitation of the stability lemma that I'm going to state here. So in the sense that, just like Igor said, we just still now we don't know exclusively on the torus how to bring to this dynamics of the resonance set all the way back to n for a very long time at infinity. That's why in order to bring that back up in the paper of Hani and so on, they crossed with R, which is dispersion, and then that controlled.
Could I ask, so in that paper, how many frequencies do they have to take initially? Is it the same story as your paper?
All of them. So you have to excite. It's not just all of them. Yeah. I believe. I will double check, but all of them. Because they are kind of independent, yeah, so in each one of them, you start with the first, and then it covers the annulus. And so you have to excite the one annulus and K. You need to have the beginning in there, yeah. OK, so this is stability lemma. And we're going to let sigma be a small quantity, less than 1, and a B large quantity. And we assume that the time, we are in an interval times 0 capital T, where capital T is basically of the order b squared log b. And now we're going to let gt, this is a sequence solution to I g dot t, gn, okay, dot, and then the usual thing, but no restriction in being resonant. Gn3 e to the I omega 4. So omega 4 is is this. I call omega 4 just because there are 4 frequencies. Plus, there is an error, E of t. And then, of course, we have the initial data. It's some fixed G0n. So let's say that GT solves this. And we have the following, that GT in L1 is not important. It's an L1 norm. But this is small for all t in that interval. And also the error is small. L1. Okay. Again, and for the same all t. Then this says then if AT is the solution to that system, let me call it star, but with the A of t equals 0. So what that means is really A is the solution of the NLS, right? Because there is no error. It's basically the NLS that you have. Okay, so if A is that, and they have the same initial data, A0 is equal G0, so same initial data, it follows that they cross. In this norm, AT minus GT less or equal than B. One assumption which I didn't put here is that this is compact support. Yeah, it just sits in a box. Okay, so what is the purpose of this? So in our application, what is ET? ET is going to be, so my system, basically the toy model, or the subsystem of the toy model, is going to be the one where ET is the non-resonant part, and the rest is going to be the resonant part. And so eventually, when you do the application, you want to prove that the non-resonant part of your system, it's small. That's really, so I'm going to go to that in a second. Now, so in the application, eventually, how do you use this theorem, or this lemma? So step one, well, you know, nothing in the toy model, nothing is small, right? I mean, we have our dynamics of the system. I say I'm going to take something close to torus 3, and I bring it to torus Tn minus 1. But that element is the x3 that I mentioned. It's not a small norm, right? So you need to do some kind of rescaling. So we do that. So there is going to be a parameter lambda. And this parameter lambda is going to make the L1 norm, if you want, small. And you can do this because this is not a critical system. We have a lot of regularity, so it's not critical. And then step two, how do we apply this? Well, we need to show that this quantity, the sigma, is small. Of course, you're going to do with this parameter lambda here. Now, what is E sigma for us? For us, E sigma is the non-resonant, where E sigma is equal to the sum. I'm going to call it, let's see, in this notation, N1, Gn2, Gn3 bar, and then here e to the I t omega 4, and omega 4 is greater than 1, greater or equal than 1. We are in the natural here, and it's rational. If it were, it's a square, so if it were rational, this could be arbitrarily small, actually, in the rational case. But here we are definitely, we can say that's not 0, hence it's going to be greater than 1. And how do you achieve that? Just briefly, I'm not going to do the proof. How do you make sure that that stays small? In practice, so what kills you is the integral in t, right? So that's, remember you had to go all the way to capital T, and capital T is pretty big there. So the way you achieve it when you do the integral, you can guess what it is. So from 0 to t of this quantity, Gn1, Gn2, Gn3, e to the I t omega 4. Sorry, let me put here sigma. The sigma. How do we do this? Well, this now is not 0, so we can do integration by parts. And when you do integration by parts, there is one piece which is at time 0, and that is whatever, it's small, and it's, you have it. And then there is one part in which the derivative hits one of this guy, and then you put your equation, and so you are expanding the number of functions in the integral that are assumed to be small. And so the more you have, and that's how you do this. So, all right, so I'm going to stop here with this. And let's see, what else do I want to say? I guess that's it. So putting all of the stuff that I mentioned together, we prove the theorems that, almost all the theorems that I stated last time, which was this mild growth that I remind you today, this more log growth that you have for the resonant part. And then I'm not going to do the proof of the theorems in which if you cross with R, you can substitute this kind of stability lemma with something which is much more global and obtain everything. So in the last 45 minutes or whatever this class, I want to mention a little bit a completely different way of understanding what we call forward cascade. So in all of this stuff, if you remember, the reason why we're interested in the growth of the Sobolev norms really came from understanding whether the following pictures can be done. So let me call this, so let's go back a little bit. This is at time 0, and what I'm representing here is the Fourier coefficient at time 0 square. And this is k. That's where k is. So the question is, can we find our initial data such that when we evolve at later times, this is t much bigger than 1, this spectrum, in fact, it's moving to higher frequencies. It's going to move in that direction. So for me, the spectrum, energy spectrum, is just the collection of the Fourier coefficient. So one reason why we study the HS norm is because the HS norm really it involves all of this element of the spectrum multiplied by a weight that should emphasize if there is this motion from low to high. But would be much better if actually we can find an equation that this spectrum satisfies. Okay, so how do we find that equation? So that's the wave kinetic equation. In order to get to that, we need to impose some kind of a probability background. And let's start by telling you that. So can we find an equation?
By the way, so this kind of results also, you think that probabilistically it should be a lot easier to find solutions over there?
The major, maybe Bjorn can correct me, but in my view, the major obstacle, if you start doing probabilistic, like let's say you assume with kind of random initial data, is to understand how the randomness propagates when you have a nonlinearity for long times. For short times, and that's the point of what I'm going to do today, because we're going to start, in fact, with random. There is a probabilistic approach, and there is a random initial data, which I will explain today. My understanding is the only way we know how to do this now is by using Duhamel and doing more and more expansions, bunch of trees, and try to find cancellations among them. That's what's going on there. And here is done, I'll give you, in fact, I hope to manage to give you half a proof of some kind of an idea of the proof of what physicists do to figure out what this equation is supposed to be. And then I'm going to tell you what the challenges are if you want to make it rigorous.
Just in the deterministic case, it's actually a deterministic, a coherent transfer of energy. So you are actually making a blob, and the differential rotation in this system transfers you, and maintaining that in a
random
case
setting.
Really great. So in other words, you're really following this blob and then exciting another blob.
Yeah. That's totally deterministic
so it's really
event.
hard to imagine.
Yeah.
On the other hand, what you can imagine, and it brings analogies with things in fluids, with cellular flows and diffusion in cellular flows. You can imagine that a small diffusion might do the job, but then you have to wait until the time before the time the diffusion actually tells you that now we go to zero.
Yeah.
So that's that might. So there is a connection between the diffusion and
Diffusion goes against that case, right? Because
I should mention that this thing about the growth of Sobolev norms is also connected. I didn't mention here. It's also connected to people working in more in a Gibbs measure kind of thing. How are they called those measures? Quasi-invariant. Thank you. So the Gibbs measure is based fundamentally on the kinetic and the potential part, and that's conserved. But if you, for example, construct instead of the Gaussian measure, you construct a measure in which you use instead of the kinetic part, hence the H1, you use an HS norm. That's not conserved, but it's quasi-invariant or quasi-conserved, and so that there are results from that proving that quasi-invariance. You're basically going to prove that there is not much of a growth. So like, for the Gibbs, you take some set of initial data and you flow them, and that measure the same as the measure of the flow. In the more, like in this other kind of measures, you don't get the same measure at the end, but you can control it, and you can use that in order to, probabilistically that has been done. For NLS, too?
Yeah.
No.
Just in 1 and 2 dimensions.
1 and 2 dimension, yes, wherever you can make sense of those measures, yeah. Okay, so can we find an equation for, well, let me just say in this way for now, for the energy. Let me just say for this is just roughly speaking for this. So because if you have an equation, then you can just start an equation and see what happens. So in order to do that, we need to impose some kind of probabilistic approach. And the starting point is the following. So we start. Now, of course, there are different kind of energy spectrum, right? This is related to my Schrödinger equation. You can do other kind like Benjaminiano or KdV or other wave or all that kind of stuff. So depending on what is your, where you started from, you will get, of course, the appropriate equation for the spectrum itself. So we're going to start with the Schrödinger because that's what we have been using. So we consider, again, our favorite equation, but we're going to put here an epsilon that is going to go to 0. This is called weakly nonlinear, NLS. And we also assume that x is, I'm going to put myself in 3 dimensions, but you can be anywhere you want. So it's 0L to the 3, periodic. Okay?
In 3 dimensions?
In 3 dimensions, yes. So we're going to have these 2 parameters. And for us, in our derivation, we're going to let L goes to infinity, and then we're going to let epsilon go to 0. And like I mentioned, there's supposed to be a probabilistic background. And what I have read, at least in the papers, like Nazarenko, for example, that have derived these equations in a formal way, I would say, in a more formal way, we assume that the initial data U0 is a random phase amplitude. So random phase amplitude field. That's how they call it. So in other words, I have my U0. I'm going to, well, I should say this, actually, the Fourier transform. So I have this guy, K, and this is going to have an amplitude. I'm using the notation from the book, so the Nazarenko in particular, and then K. And then we're going to assume that the JK and the FK are random variable, and they are independent. Okay, this is going to be helpful later on when I'm going to do the rest of the work. And so at the end, what you're going to look at is you're going to have an F, L, epsilon. This depends on epsilon L.
Is phi k uniform variable on 0 on the torus?
Assume what you want.
No,
Yeah. I like it, very simple things. And then what are the more complicated assumptions? I'm really not good enough in probability to tell you what. There is a more expert than me, Bjorn, there that can correct me. Anyway, so we have this. Let's say this is the following. It's the expectation of my U0, sorry, my UT. That's the solution that we get, square. It's going to depend on L and epsilon. And you're going to have to reparameterize the time. You will see. But let's just don't worry for now too much. And now what you want to do is take the limit as L goes to infinity and epsilon go to 0. And you're going to get an F here. OK. What is the equation that F satisfies? That equation is the wave. So F solves.
Is there something special about the way you do it?
Oh, yeah. It's all well, OK. So in the informal derivation that you find in the book of Nazarenko, actually Nazarenko does the derivation for a different kind of equation. It's ZK, but never mind that. You can repeat the same thing. In there, first L is sent to infinity, then epsilon is sent to 0, and they are not related, like in the Boltzmann, for example, in there. In the work of Deng and Hani, those two are related. They are, some power, inverse powers of each other or something.
We're going to mention Zaharo, right? I mean, we're going to
Oh,
say
yeah.
that, okay,
No, yeah.
These things are not...
No, this is, I mean,
from other.
the rigorous one, okay, I'm not going to go to the history, the whole history, but the rigorous one, it's like when you take all the limits for all your diagrams that you get. That's by Deng and Hani. Okay. So F solves the wave kinetic equation.
They have the equations for it.
That looks like this. So let me tell you how it looks like. Yeah, there is a lot of work on that. Okay, so the equation is dTF equals QF. I'm going to, oh no, not QF. And then we have F at 0 is some F0. And by the way, these are positive, obviously, not negative, because they come from, expectation of something positive. So, but what is this Q? And the Q, I think I'm going to take another blackboard because it's pretty long. By the way, this is only a forward. This is only a forward equation, right? This is okay. So Q. So this is the integral. I'm in dimension 3, as I mentioned. So 3 of dk1, dk2, dk3. So these are no longer discrete. These are now in the continuum. Although I'm using the same notation in order to, connect. Then delta k minus k. I think here is k1 plus. Okay, let me just write it like this: minus k1 plus k2 minus k3. This is going to be the usual. Convolution tells you that you're going back. You are using the cubic NLS. Then there is another delta function. That's about the resonance, and that's k squared minus k1 squared plus k2 squared minus k3 squared. And then here you have a combination of, okay, I'm going to use the following notation. When I write Fi, what I really mean F at Ki. Okay, that's my notation. So F2, F3, F1 minus F. There are some symmetries anyway. I'm not going to, you might see it written a slightly different way, but there are symmetries. And that's it. So that's the Q for this thing. This is called the 4-wave kinetic equation because there are 1, 2, 3, 4 waves interacting. Okay, so now let me tell you an example of what do we know about these things, this kind of system here. So there is a lot of work that Escobedo Velasquez did on this. So I want to mention that. So they worked on the, let's call it well-posedness of this kind of equation here. And I can say that up to this moment, there are only results if we assume that you have a radial symmetry. Okay, if you don't have that, we don't know anything. So that's what it is. So let me give you a typical theorem. By the way, I want to say that if you have a different kind of equation, instead of the Laplacian there, you have a different kind of operator, then that will bring the difference here. And then, of course, the theorem will change depending on that. But anyway, let's just state for this. So assume that F0, this is the radial itself. So I'm going to write it like this. It's greater or equal than 0. And so the obvious type of assumption that you would like to keep here is what comes from the conservation law of the system you started with. So you will recognize this. So we have F0k dk in R3. It's finite, and this is the mass. If you think about it, this is the mass. Let's call it m. It's finite. And then what you expect to be the energy. So the energy for us is, remembering what this F is supposed to be, finite. That's the energy, right? Because we are looking, these are really Fourier transform type of thing, Fourier coefficient. So this is the assumption for the initial data. Radial, mass and energy are finite. So let me tell you that first that we know that there is a solution, then I have to write for you what that means to be a solution. Okay. So let me first state the theorem, and then I'm going to tell you what. Then there exists a global, mild, what we call mild, solution, which is itself radial. Just denote it like that. But the interesting thing is that no uniqueness here, we don't have any uniqueness, such that the limit as t goes to plus infinity of, so if I take this quantity and I'm taking okay, so this is 0 for all r. Oh, okay, well, yeah, greater than 0. Okay, so what this is telling you, yeah,
I'm sorry, apologies.
no, you can.
No, I'm just asking stupid questions. Sorry.
Okay, so, but
can
nothing
ask
is,
later, maybe.
okay, that's good. But what this mild solution that is obtained, you see it when you take the limit at t goes to infinity, it's always outside a large ball. And this is the forward cascade, right? Remember, this is the k's are representing exactly, so everything it's kind of getting farther and farther away and outside the ball. I'm not going to prove this theorem for you, so I'm going to leave it here. But this is the typical type of solutions, and there is more than these results, of course, but I just wanted to give you an idea. Now, I didn't tell you what solution means. So what is a mild solution? So mild solution means that the following happens. I didn't tell you, sorry, I didn't say where this lives, just for completeness. This is C1, 0 infinity in time into L1. Okay. Being the solution means the following, that for any phi, okay, smooth enough, compact support, and I'm going to assume that also this is radial. Of course, integral in R3 of ftk phi of k dk is equal, well, the initial data, f0 k phi k dk plus the integral 0 to t, integral in R3 of the nonlinear part, if you like, dk. There is a sigma here. Let me write the time like that. So that's what it means to be a solution.
So some kind of distributions.
Yeah, mild in this, and no uniqueness is known or anything, just like
There
that.
is no
No.
Sorry.
Yes.
Presumably it's not the same T.
Presumably it's not this. Oh, no, that T. No, very good. So you mean this one? Absolutely. In fact, I'm going to try now to give you an idea of the derivation of the thing, and you will see how you have to rescale it. Yeah, absolutely. So, so some people are trying now to figure out what's the connection between this and the Sobolev norms, the growth, and all that. So, so the rest, it's going to be, unfortunately, a little bit of a process to derive the wave kinetic equation, but at least I want to give you the formal argument. And then you understand why the rigorous argument is not that simple at all. By the way, I just want to say that there is also a companion wave kinetic equation, which is called three-wave kinetic equation. And that is, for example, what comes out if you use the zk equation, which is sort of a higher variable, higher dimension KdV type, which has a quadratic nonlinearity. That's why you end up with the so-called three-wave. So the Q is different. Instead of having 3 functions in there, it's going to have 2 functions. And for that, with Bin Tran, my collaborator, we do have a result for non-radial. But yeah, just want to say that in general, that's all we know, radial. Okay. Say it again?
And the K knows out uniqueness?
Oh, yeah. Yeah, we don't have uniqueness, correct. Okay, so let me tell you how we start. So now we attempt the non-rigorous derivation, or I would say the formal derivation of the wave kinetic equation. So formal derivation of wave kinetic equation. All right, so like I said, we start with NLS, and as we did also last time, we're going to look at the Fourier coefficient. So we'll start, let me just write symbolically the process, this first part of the process. Remember there is an epsilon here. Okay, and then we pass to Fourier transform, and we get UTK, we're going to call it AKT. Then we do the type of little gauge transformation that we did last time. We're going to call BK to be AK e to the I omega k t. For me here, omega k is nothing else than k squared. Okay, of course, if you change equation, it will be a different thing. All right, and now this will give us the following equation. I b dot k, we have seen this before somehow. There is an epsilon, and then the sum k equals k1 minus k2 plus k3, and then bk1, bk2, bk3, and what we have to record is this. Okay. That's where we start. Now, sorry, this is a little bit more complicated than that. This, okay. Okay, 2, 3. Okay, let me tell you what that is. For me, omega k, 1, 2, 3, there are going to be a lot of indices, so I apologize for that, is omega k minus omega k1 plus omega k2 plus omega k3. Okay. So far, so good. Now, we want to go, by the way, we have an initial data here as well. So I'm going to call it, let's assume that, let me write it here. So B k at 0 is A0k, my initial data. And this is the one that has the random phase amplitude kind of thing, and we're going to use it later. All right, so now the goal, as in many of these things, is to write. So we want to write BKT as an expansion in terms of epsilon. So there's going to be an epsilon 0. So I'm going to just for you recall like that. BK0 T plus epsilon BK1 T plus epsilon square BK2. And so on and so forth. In this type of argument, this derivation, you wanted to get it for up to epsilon to minus 2. So let me record that. This is the kinetic time. Is epsilon to the minus 2. So you want to do the derivation. And if you want to stay in this range, let's say, you can ignore everything else that is epsilon cube. I mean, that's what we say. We can ignore. So we just do everything up to order epsilon square, and everything is going to be ignored here. Now, that's the difficulty of doing this rigorously, that you have to prove that everything that comes from epsilon cube on is actually going to 0. Now, of course, epsilon cube seems like go to 0. That seems like a large enough power. So, seems feasible. The problem is that there are a lot of terms that accumulates, and that's the difficult. I mean, that's one of the difficulties. But let me move on and tell you how do you, well, you now patiently try to figure out what are, so we need to find B0, okay, B1, okay, and actually for us only B2k. We don't need anything for this formal derivation. That's all we need to do, because we're only going to stop at epsilon square, and we abandon everything else. Okay, so it's pretty simple to do this argument, because you see that when you, how do you find those coefficients? Well, you plug back into the equation, and then you match the one that have the exponent that is the same. So for example, B, you get B dot 0, k to be 0 from doing this matching, which then tells us the only possibility is that bk 0, it's a constant, and in fact is the initial data. We got the first one. Now let's just, to get used to it, let's try to do what happens to the next one in line. So this is I, B1, that's the one we want to look at. This is going to be the sum k, k1 minus k2 plus k3. And here there is a B, these terms 3 times, but I know that already that they are like that. So I have a k1, a k2, a k3. And then there is the e to the I omega, my notation k, 1, 2, 3, t. And the initial data is going to be, for this particular thing, is 0, because we already took care of the other one. We solve this easily, and we get the following. So that B1, let me say at capital T. So my capital T actually is going to be, as we'll see, will be some tau, where tau is going to be small. So that's where I want to get to that point. Okay, so this is going to be up to constant, which of course I will always ignore. Let me put a C here. Sum k, k1 minus k2 plus k3, and then a k1, a k2, a k3. And then we have this integral, integral 0 to capital T of e to the I omega k 1, 2, 3 sigma the sigma. And since I'm going to have to carry this with me sometimes, I'm going to call this delta T of omega k 1, 2, 3. Okay, last bit is the last one.
This procedure tries to find the entire solution, but you are only after the energy, right? You're after only the multiple squared of
the multiple square, so, exactly, only that.
Right. So,
but you need
doing it like this, you keep keeping together things that are going to cancel.
Absolutely, absolutely. There's going to be lots of things that will cancel, and lots of things will cancel because we are assuming the independence of the amplitude and the phase. And lots of things cancel because symmetries. So there is a lot of...
Well, maybe my question was, wouldn't it make more sense, or at the level of an expansion up to 3, does it make any difference if you put from the beginning an expansion only for the moduli of the guy squared, and not the whole thing? In other words,
yeah, let's you will see what it comes out in a moment.
No, of
yeah,
course
yeah.
It, but there are pieces of it that will cancel.
You will,
so
yeah.
From the beginning,
I guess if you know, sure. But like me, I didn't know this at the beginning. I went through the whole process of doing this. Yeah, in retrospect, and I think this is helpful, especially when you wanted to go and expand everything. I mean, you want to put fewer and fewer terms. So if you see things that already shouldn't be there, that's But this is the naive thing, so let's now go to the 2. And I'm going to just, for you, I'm just going to write it down already what is the equation and immediately the solution. So this is I b dot 2. Oh no, I guess I already, no, this is the, yes, t, there's a dot here. So this is the sum. And you will see that there are now k1 minus k2 plus k3. And you see a bunch of combination. And you see it's getting harder and harder. So 0, bk2, 1, bk3, 1, and a bunch of other things. But you can write them up. And of course, e to the I omega k 1, 2, 3 t. Okay, so when you write it down, this becomes an expression.
Sorry, I'm just confused. Should there be 2 1s and a 0 or 2 zeros and a 1?
2 1s. There are more than that. So there is a 0, 1, 1, a 1, 0, 1, and a 1, 1, 0 in the other one. Be more? I don't know. Maybe. But let's just. This should. Let's see.
2 zeros is 1 1.
2 zeros.
There's an epsilon in front. And
Oh yes, this is the epsilon square. Whatever gives you the epsilon square.
it's 2 zeros and
2, 0, and 1. All right. Okay. That's there is some expression here that you write it down. Now I'm not going to write this because it's going to be too long. But of course you have to do it. But one thing that it's interesting, you see that once you are in this term, you have you start seeing the Feynman trees, if you want. So in other words, we started with a k, and then when we looked at the first one, you get k1, k2, and k3. So this is k, this is k1, k2, and k3. And you should record also the sign in a sense. So you can make it sure that, for example, you declare at the beginning if it's positive, it goes this direction, negative goes in the other direction, but you should record that. And this was for the expansion to find B1. But when you start going to the B2, what you're going to see is the following. So, okay, there is the K, there is K1, K2, K3. But now this is going to split again. This is K4, K5, K6, and then you have another tree, which is, you have to sum with this, which is when you split the one in the middle, and then the one on the far right, and so on. Okay, but these are the fundamental tree that enters in the wave kinetic equation. But if you imagine doing this for all the B's, at the end, you will see a different kind of trees that come in. And another difficulty, and maybe what helps in order to control these remaining pieces that are with the power epsilon cube and above, is the fact that you have to, remember, this is only one piece. You have to match with another one. That's what it is, what you have to do. You have to do the meaning of that. And you have to try to understand what is the cancellation that happens among these graphs in order to conclude. Otherwise, there's going to be just, if you do one by one, there's going to be just too many and you will not control anything. But let me just tell you a little bit where does these delta functions come from and so on. Okay, so once you did all of this work, you wrote everything down. Now you have to compute things. So let me just make a definition. So I'm going to call f of k to be L to the D. There's going to be some other constant floating around, but those are not important. And the expectation, if you want, the mean value of the JK. Remember, JK was, so JK from, do I still have the definition? No. So JK is BK square. Okay? All right. So we have to do that. So we write that. And this probability, this expectation that you take is with respect to...
These three here today.
Say it again?
These three.
These three today. Yeah. But you can do for any D. Okay, so this, as just by using the definition, is LD of expectation of BK square. So now, when you write it down, so now forget the D for L to the D for a second. Let's try to write down this. And you have all your, of course, you have B0 plus epsilon B1 and so on. And you have to multiply with the bar of the other one. Okay. So now there is a bunch of, and there is, of course, now there are a bunch of pieces that you have here. And again, you're going to take, this is going to be the one with epsilon 0, which is just this, which is the initial data, as we recall. So this is just a time 0, the initial data. Then there is an epsilon, and then there is an epsilon square, and so on. Okay? Now, let me tell you a little bit just an idea of how the probability comes in and how does this help you. So let me just remind you a few things that happens when you assume that you have the random phase amplitude. So some probabilistic idea, okay? Facts, let me call it facts, just for you to have an idea. By the way, this that I'm gonna write it down works a lot. I mean, it's easier if you have, instead of a cubic nonlinearity, a quadratic nonlinearity. But I just want to give you a sense of what happens here. So for example, if you have this BK1, BK2, BK3 bar, and actually let me first state a theorem and then we do a couple of examples. So there is a lot of cancellation. For example, coming from this weak contraction, whatever it's called, weak contraction rules. So this is very handy theorem. It says the following. So if I have RPA field, then when I have, for example, BL1, BL2, and so on and so forth, and then the bar of them, let me call this BM1, BM2, and so on. So a bunch of these things, some with bars and some without bars. So this is 0 if, let's see, if the numbers of bars equal numbers of non-bars. Okay. All right.
Assumes
Not, say it again.
It's not equal. The number of bars is not equal.
Not equal. Okay. Not equal.
Right.
Okay.
And this
Thank
one
you.
doesn't assume Gaussianity. Gaussianity will give you more precise information.
Yeah. That you can, yes. This is just with RPA.
It's just the fact that the phases are independent. And
So this is one thing that we use, that is used in here. And let me just do a little, for example, one calculation. All right, so one example. Thank you for, all right. So for example, suppose we have this, BK1, BK2, BK3, bar, BK4. Now, this is going to be, it's going to have each one of this as an amplitude and a phase. So I'm going to, and they are independent, so let's just separate them. Dk1, dk2, dk3 bar, dk4. First I'm going to do with respect to the phase, and then with respect to the amplitude. Now they separate because, thank you, yes, that's one has a bar. Thank you. So this is the case in which it's not zero. All right. So now this separates because they are independent. And so each one of them, as I have been written, has a, remember, bk1, ki, this is square root, the way I indicated, 1 and then phi1, phi. That's how I wrote them, okay? So they become square root of j1, j2, j3, j4. And then we have phi1, phi2, phi3, phi4.
E to the I, right? So it's still, it's still exponential.
Ah, still exponential. Yes.
E to the, yeah, yeah.
But it's the same. Okay. All right, so I'm going to write like this. Phi. Okay. Now, let me just proceed to give you. So when you do the phi part, let's pretend to be physicists. Okay, so so the phi part, so phi1, phi2, phi3, phi4, or whatever. So maybe I should, with I, yeah, because I need to record. Okay, I'm going to just put this to say that with the I in front it's minus. Okay, let me just do that. Okay, so this thing, phi, let's see if we did it correctly. So this, I claim that is a delta, this is delta function. 1, delta 4, 2, plus delta 4, 1, delta 3, 2. Tell you in a moment what these guys are. 1. That's what I claim. I see. 3. Now I cannot read my handwriting. Maybe it's a 3. I'm not sure. Okay. Okay. Let me say first what it is. Delta ij is 1. If ki is kj, and 0 if ki is not kj. Anyway, I'm not sure what the index is there. I cannot read my handwriting. Okay, so then you go back to the j that you have. This should be done with respect to the j. I might have missed something.
You need to assume just a little bit, like some trivial words like mean zero.
Probably. I don't know, Igor. Probably, whatever you want to assume, let's assume that, yes. Okay, so then you go back to your j, and then at the end of the day, my claim, let's see if this is, this whole calculation should give you the following. Should give j1 square minus 2 j1 square outside, of course, and then delta 1, delta 3, 1, delta 4, 1, plus. By the way, this is just to give you an idea of what kind of the assumption of random phase amplitude can give you. Plus, I might have missed some exponent, but that's what I wrote. Okay, this was just an idea to tell you what kind of calculation you can do with the assumptions. Now let me go back to our calculation, and unfortunately I'm going to have to cover this. But using this type of thing, you can prove that this is 0. There's nothing in there. So you remain only with this initial data and epsilon square with certain terms. And I will estimate for you only one of them that is here. Okay. Maybe actually, well, just do this. So let's see if I can complete. So I'm going to quickly write So let me just, using this, now I'm just gonna, I said that you can prove this is 0, and there's gonna be a term here that I'm gonna write. So you get the following. You get bk, capital T, well, first with respect to phi, and then with respect to j, if you like, minus, you have the initial data, b0k square 0. I didn't put square here. Okay. Phi. This is already at 0, so that's maybe to make it more compelling. Let me write this. Just you see that that's at 0, and then this in j. And this is equal. So everything, I already put the initial data here. I said that epsilon, the term with epsilon goes to 0, so we have some constant which is not important, then epsilon square. And then the sum k1, k1, the usual sum. And then I have only j, k1, 0, j, k2, 0, and j, k 0, so that's a 0. J, and then that term that I call T 1, 2, 3, and there are 2 squares of that. There is a little bit more, but let me just stay in here. And so the let's also assume, to make things a little bit easier to write this part, that k1 is now equal k2 and k3 is now equals k1, k2. So this separates into just expectation of each one of them. K3. And this guy we have called them f of k1, f of k2, f of k3, but there was some d that needed to be put in there. So this is 1 over d, L, sorry, to 3d. Okay, so we just replace them. Okay, we're almost done. We take the limit as L goes to infinity at this stage. And when you do this sum, so the 1 over L to the 3D, and then the sum k equals k1 minus k2 plus k3, well, this is going to tend, as L goes to infinity, of the integral in R3 of dk1, dk2, dk3 with the delta function k minus k1, k2, k3. And that's where the first delta function comes in. And the last bit, which is just 1 minute. So let me just finish this. So now is the time that we have to think about. Okay, so now when we write, I can rewrite this also in terms of f's, and with the d in there. So we get the following. So f k t, let me call it, okay, let me just, okay, so now let t equals epsilon minus 2 tau. And remember, there is this epsilon square here that I can use it to, so I'm trying to go fast, but somehow, so let's see. My notation is, let me write the following. So let's write f k epsilon tau equals f k epsilon minus 2 tau. We write it like this. And then we have that f by rewriting everything, epsilon tau minus fk epsilon at 0 divided by tau is equal to the integral in R3, this delta function, k minus k1 plus k3 minus k4, k1 minus k3, dk1, dk2, dk3, and then we have the f's, the three of them that are here, rescaled in this way, so tau fk2 epsilon tau, k3 epsilon, and this. And so the most important piece was this guy here. So this is delta t, but now t is epsilon square minus 2 tau square. And since I'm going to divide here by tau, I divide here by tau. And remember, there was an epsilon square, so that comes down here, minus 2. And if you take the limit as epsilon goes to 0 of this will give you the delta function, which I wrote before, omega k minus omega 1, omega k2, omega 3. And that's the end. Now, this is not quite f dot, which is what you would like to have, but that's, a tau is small, that's the derivative. And this is the right-hand side of the wave kinetic equation. And that's it. Thank you, guys. Yeah, this was too compressed, but it's the hard part, so you don't want to see probably more than this.
I'll ask you private.
Yeah, but you should have.
Are you tomorrow?
No, I'm leaving tomorrow. I'm going for a little trip with my daughter. It's a spring break.
Next week, Monday, Tuesday.
Not here next week.
Oh,
That's the
okay,
same.
then I'll be there.
Oh, when are you back? Then we have to. Perfect. That's actually when.
Okay.